We can.
Okay. So our today's speaker is Sofia Kantorovich. She's a professor at the Ural Federal University in Ekaterinburg in Russia, and also is a senior research and group leader in the Faculty of Physics at the University of Vienna in Austria. Okay. Her just to give just a general overview about her research, mainly focusing what is actually known as complex dipolar systems. And let's say just to give you a rough idea what this is about. It's mainly about charge, soft matter, for instance, unit liquids, or the study of the behavior of polyelectrolytes, and also magnetic soft matter, for instance, magnetic colloids, magnetic liquids, the behavior of magnetic filaments or magnetic polymers, etc. She will give us a talk about magnetic soft matter in analytical theory and simulations, in which she will show us how bringing together statistical mechanics and massive or extensive numerical simulations in many cases, we can have a better understanding of the behavior of these systems and probably help experimentalists in their development of novel and smart and promising new materials for the technology. So, whenever you want.
Thank you, Tomas, for your introduction. Careful, fingers. It's the second time I'm here for a long stay, and I always really enjoy. Not only because the island is beautiful itself, but also because it means for me to visit like very old friends and actually their families now, and it's a real pleasure, so I'm very happy to be here. Yes, it's true what Tomas said, and we will be talking about magnetic soft matter. And the overview of the talk would be the following. So first, I would try, in rather general terms, explain you what we need to know about both soft matter and magnetic interactions, actually in order to incorporate them together, and why is it good in general. Then we would try to go step by step, actually rather historically, following the development of the ideas in magnetic soft matter. And then we would see how the correlations between these magnetic particles would actually affect the structure of the material, the macroscopic response of this material, and eventually we would see that there is self-assembly taking place almost unavoidably if the interactions are strong enough, and then this self-assembly affects drastically the properties of these systems. Besides that, we will try also to see what kind of complex colloids you can synthesize and investigate based on these basic ideas obtained for rather simple, even model toy-type colloids. The work I am presenting is mainly done by my group, which is Dipolar soft matter group, based in Vienna and in Ekaterinburg, and I will show you actually who did the work. I always show this slide because, well, we are a theoretical group, but we are working rather actively with experimentalists all over Europe. And we try to see what is the stream, what is the development of the experimental techniques. And it's rather interesting to observe that, say, 10 years ago, synthesis of a magnetic nanoparticle. What is a magnetic nanoparticle? It's a 10 nanometer crystal, which has a single domain, so it is uniformly, presumably magnetized, and can be approximated by a single dipole was a challenge. It was really a challenge. So if you wanted to synthesize a rather big, say, industrial scale amount of magnetic nanoparticles of the same size and the same remnant magnetization, that would be really difficult. That remained a challenge nowadays as well. But on the other hand, due to extremely fastly growing developments in, say, DNA origami, or in general colloidal science in the synthesis in the last 10 years, actually very interesting new magnetic systems became available. And here you can see, and also new analysis techniques. So, like for instance, this is from 2004, and that was a breakthrough picture. It was the first in vivo image of magnetic nanoparticles of the size of 20 nanometers, forming chains, kind of ring structures you can see, and being rather monodisperse. Nowadays, what you see here, this is 2012, I think, the group in Utrecht, led by Albert Philips, the same group actually. They managed not simply to synthesize extremely regular shaped colloids, cubic shaped colloids, but they have a magnetic core with a well-determined orientation of magnetization. So that's the difference in less than 10 years. Here on this picture, you see silica colloids covered with cobalt platinum nanoshell, and they are like the magnetization of this colloid is pointing perpendicular to the surface. And this is the group in Dresden nowadays, they're doing it. Then you can do pretty monodisperse suspensions of magnetic ellipsoids or magnetic Janus particles. This is from the University of New York, actually. The group is working actively on the synthesis of magnetic Janus particles. And now the question comes, so coming from 60s, where the first ferrofluid was actually synthesized, so kerosene-based suspension of a certain dispersion of magnetic nanoparticles, up to today. So what actually do we know analytically, say theoretically, what kind of basic features are there to model and to predict the responses of magnetic soft mirror? And the traditional spherical horse in vacuum, in this case, is a dipolar hard sphere. Dipolar hard sphere is good for several reasons. It's spherical, it has a point dipole, and it basically has no steric potential whatsoever. So it has a very clear mathematical shape of that potential. Unfortunately, in the experiments, they are not always hard spheres. Well, basically, they are almost never hard spheres. Why? Because if you think about a magnetic nanoparticle, and then you take the second nanoparticle, and you don't do anything with them, you don't work on the surface effects of these particles, they approach each other, there's extremely strong van der Waals attraction. They stick together due to van der Waals forces and magnetic in addition, and they coagulate. That's not what you want. So usually you somehow surfacely stabilize the systems, and it prevents this kind of irreversible aggregation and sedimentation. But I mean, steric stabilization, for instance, gives you like polymer molecules on the surface of the nanoparticle, and then the attraction or whatever, the interaction, the steric repulsion side is rather soft. And another compromise, analytical one, would be to use a potential kind of like soft sphere potential. The common feature for all these point dipolar particles would be a dipole-dipole interaction. The good thing about dipole-dipole interaction, or an interesting thing about point-dipole interaction, actually, first of all, a very important remark, as long as the word polyelectrolytes and charges already sounded today, two uniformly magnetized spheres interact exactly via this potential. There are no higher order corrections. So it's not like extended dipoles created by charges, where you would have the complete multiple expansion for the interactions. Here you are really limited by dipolar term exclusively. And this is very convenient about magnetism, so you don't need to think about this kind of higher order corrections. On the other hand, dipole interaction as is already brings you some peculiarities, namely you see that it depends not only on the position of the centers of the particles, but also on the mutual orientation of the dipoles, and can change accordingly from repulsion to attraction. We use usually the parameter lambda, and I want you to remember this notation here. We will use it throughout the talk. It's the ratio of the magnetic energy of two head-to-tail aligned dipoles at a close contact to the thermal energy normalized by the diameter of the particle. So basically it shows how strong is the dipole interaction in comparison to thermal energy. That's kind of a characteristic parameter for dipole soft matter in our approach. And then of course we are wondering how many items, how many beasts you have in your system, and the regular dimensionless parameter would be like a volume fraction or a number density. So I would use this kind of dimensionless value here, which is basically almost the volume fraction, just it doesn't have pi over 6. But I mean, that's a matter of habit. If it's not specified, it will be wrong. So what happens if actually you look at the interactions? The interactions tell us there is a minimum, 2 cell points, and a maximum with corresponding values of this energy, like -2, -1, 1, and 2. And then another energy, which actually should be there because we want to control magnetic soft matter. And in order to control this, we need an external field. And it was not Peter Zeeman who decided to call the energy Zeeman energy, but it's called Zeeman coupling. And it tells us that dipole moment wants to align along the magnetic field. And this is the main tool. So this 4 orientations plus this additional term, linear with a dipole moment, would be our palette to actually try to create a certain response of this material, and to probably alter the properties of the basic building blocks to actually produce a response we want. And initially, what you want to do with magnetic soft matter, you want to magnetize it. And that dates back to the end of the 19th century, and the name of Paul Langevin has to be necessarily mentioned here, who in 1901 proposed the standard model of superferromagnetic gas, which tells you that the curve, the magnetization curve, actually looks basically like that, so a standard Langevin curve. So the total magnetic moment of the system as projected on the field axis, as a function of a dimensionless Langevin parameter, which is the ratio between Zeeman energy and the thermal fluctuation, has first a very rapid increase and then a saturation region here. And these two regions are very important for the characterization of the material, because this shows you how the material reacts to a weak field, and this how actually it is finally magnetized. So saturation, magnetization, and initial susceptibility are two very important parameters. And the most interesting so how the process of magnetization in general goes. So imagine a gas of dipolar spheres, dipolar hard spheres. You apply a very weak field. We know that the interaction with a field is proportional to the dipole moment. So what happens first is that big particles say, oh, I feel the field, and they start rotating. The small particles are too much disturbed by thermal fluctuations to actually react and turn. So this part of the curve is provided by the reaction of the largest non-compensated dipoles in the system. Whereas this part is already really like very strong field tries to fight thermal fluctuations in very weakly dipolar particles. Which means that if I have a non-compensated dipole due to self-assembly, presence of polydispersity, presence of larger particles, it will be all reflected here. Indeed, if you look at the standard Langevin value of the susceptibility, you will actually get that susceptibility as a function of temperature with decreasing temperature would grow. What is actually the Langevin assumption? Is that every particle only knows about the presence of external field and does not correlate with any other particle in the system. So that is what is ideal supermagnetic gas. And please look at the value. The values at this dimensionless temperature would be approximately 2.5 and will grow with growing concentration of magnetic material. Instead, if you now employ it's not directly a Weiss model, so it's not mean field we know from solid state, but it's a similar approach which would give you the initial susceptibility as a series of Langevin susceptibility, and it only tells you that each particle knows that there's not only an external field, but the field created by the neighboring particles. So basically, if two particles around me turn, I feel an additional torque due to the additional field to actually realign my dipole moment along the external field. And this kind of approach would give you, for exactly the same systems, the value of 5. So it's only mean field correlations would increase the susceptibility by the factor of 2. Now let's see what happens actually if the temperature is so low and the dipole interaction is very strong. Then head-to-tail orientation of the two dipoles starts being so advantageous energetically that actually the self-assembly into chain structures will take place. And now imagine you have a chain and you apply a weak field, and this is a huge non-compensated dipole. So a chain as a correlated object would contribute to the initial response dramatically. So it would, of course, as a completely correlated object, will somehow turn or realign itself to the external field. How do you describe chains usually? I decided not to talk about any modes here. In general, the standard thing is based on the classical density functional theory. So you need to write a free energy of a system of dipolar hard spheres, assuming that they can form chains of different length. And then as for a density, the density, which is the argument of this density functional theory, would be the concentration of chains of a certain length. And then you minimize the free energy. And the procedure is rather standard and equivalent to Wertheim's theory. And it gives you an equilibrium distribution of chains at a given temperature, given field. And it sounds rather straightforward. There are a lot of stumbling blocks and underwater stones on the way because the calculations are rather cumbersome and involving. But still, you can do that. Then you obtain the free energy at thermodynamic equilibrium. And then eventually, if you differentiate it by external field, you get the magnetization. If you differentiate it twice, you get the initial susceptibility. And doing this kind of trick, you would get the equation for the initial susceptibility, which is provided here. And of course, now my particles can form chains. I allow them to form chains, but they also know that there is an effective field. So it's kind of the next level of complexity in these models. And you can see that the initial susceptibility is again expanded in the series of Langevin susceptibility. Just now it has these two parameters. And the two parameters are rather important. P is the probability of forming a dimer, which can be found from the minimization of the free energy. And in the simplest case, has a closed analytical form. And K is the correlation coefficient between the two neighboring dipoles within a chain, which means that this is a projection of one dipole on the dipole of another, or of a neighboring particle. So basically a cosine of the angle between the two dipoles. And if you plug in this formula for the same values of of the density of magnetic material, the value becomes 50, which is 25 times larger than the Langevin initial susceptibility. So for the same system, if you properly consider the correlations and the self-assembly, you go to an increase, an experimentally observed increase of the initial susceptibility by a factor of 25. So which tells us that even on a very simple system of dipolar hard spheres, ignoring one or another type of microstructural formation can lead to really drastic underestimation of the magnetic response. And then you say, oh, but that's a miracle, right? It's perfect. I want to have a responsive system. I put in large particles, they interact, fantastic. They form long chains. I apply the field. Wow, I have a fantastic response. No. Let's cool the system even more down. Actually, this is the place where I was born. It's a bit distant from where we are now. If you go down in temperature, then what happens to the system? So a chain, what is good in the chain? The thing good about the chain is that it has two ends. So entropically, it enjoys itself, right? Pretty much. Energetically, it lacks one bond. So it can always form another bond. And now we come to the temperature where entropy starts being not that relevant, but the energy starts overtaking. And then what happens? It becomes more energetically good, like favorable, to form the last bond rather than to stay and with wobbling ends. So we form rings. And actually, if you look at the ground states of these dipolar hard spheres, say in a monolayer, we did quite an exhaustive study of these things. You will discover that a ring is actually a ground state. What is the susceptibility of the ring? Well, what is the dipole moment of the ring? It's 0. So it's actually not susceptible. So which means that a small external field, particles in the ring would not care. They would say, go. And now we need to see to which point we can push our system in terms of magnetic interactions to actually keep it responsive to an external field. And that was a challenge because you need to add to the free energy another term which takes into account rings. First we decided we actually check, are there rings? So we know there are rings at 0 temperature. And that was a challenge actually for many years. So you needed a very dilute system at very low temperature, and you need the system in thermodynamic equilibrium. Numerically, it took, well, I think we were trying to do simulations at this region of parameters for at least 10 years. We didn't manage. Well, we managed something. We had some clues. Some people from other groups also had some clues. But we needed to arrive to the point when the algorithm development basically reached the level of, so people could do perfect rejection-free Monte Carlo with properly weighted ensembles and everything. And then, actually, it was not us who did it. It was Lorenzo Rovigati in Sapienza, who first managed to get everything together, put everything together and push it, and wait for actually 4 months. And then they said, oh yeah, we see the rings. And this is cooling, and blue ones are chains and red ones are rings. So there is a complete redistribution. And at that time I was actually moving to Rome and to take over this project, and we decided, okay, we do some analytics on that to see if actually that would really work and would affect the magnetic response of the systems. And it turned out that you can analytically very nicely describe the free energy function using proper like weight of, say, partition functions, obtain equilibrium concentrations of chains and rings at a given temperature. There's no field in this functional currently. We're talking about the initial slope. And you can very nicely capture the simulation tendency for a complete redistribution of particles from actually chains, which goes from 1 to 0 to rings. It's a very dilute system. It's a very exotic system because apart from chains and rings, you don't have anything. So you are in a very dilute regime. But still you have very developed self-assembly. And then if you look at the initial magnetic susceptibility, you all of a sudden observe that there is a maximum, a temperature maximum. So on cooling, the susceptibility reaches the maximum and then drastically drops down. That is what intuitively we expected when we thought about rings, but this was a very striking confirmation from 2 points of view, actually. The first one was that you can't push the system too far. So there's just no way. There's always a limit of dipolar hard spheres. They can't be too susceptible to an external field. So you can't, if you only deal with increasing dipoles, there's no way. So this is the first thing. The second message from this plot is the following. People were expecting to have gas-liquid transition at low temperature. So gas like liquid vapor transition. And there was a 30 years debate why dipolar hard spheres, or if dipolar hard spheres undergo a standard vapor-liquid transition at low temperature and high density. Had it been the case, you would have seen the divergence of the susceptibility, because this is the second derivative of the free energy. And as long as the formation of rings block the growth of the susceptibility, that's the first clear and very neat sign for the fact that the phase diagram of dipolar hard spheres really lacks this point. So there's no vapor-liquid transition, at least for the range of parameters which we investigated. And that was a quite interesting feeling, and we decided, okay, but then we go denser. No, okay, I mean, that's at the end of the day a very artificial system because we diluted it by like, I mean, you can't even synthesize this. You wouldn't measure anything. I mean, it's just like the response is far too weak. And we went to a denser system, and there was also a, like, in the beginning of 2000, I think, Safran did an analytical model saying that there is no vapor-liquid transition in dipolar hard sphere systems, but there is a different kind of structural transition between open ends and wide junctions. It was paper in, I think, Science 2000. I don't remember exactly, 2000 or 2001, Tatley and Safran. And there was really like an avalanche of people saying, yeah, we observed wide junctions are great. Wide junctions have 3 ends. I can wobble with 3 ends, so it's entropically fantastic, energetically additional bond because you have a triple point. And the theoretical model is very nice and very clear and, I mean, sweet, let's put it like that. The only problem is that there's no ring formation taken into account. So what Safran missed at that point, and that was clear because it was just shortly before people started seeing rings in the simulations, he missed rings. And rings cannot form wide junctions because they don't have 3 wobbling ends. They actually don't have any wobbling ends, right? And with my colleagues in Rome, we put a serious effort to actually try to classify the junctions which we observe and branching points which we observe in dipolar hard spheres. We are still dealing with a very simple toy system dipolar hard spheres. And then what we observed, that yes, indeed, there are three-way junctions, so which have three ways out. But there are several more junctions which should be necessarily taken into account. And those are, for instance, four-way junctions, and they can connect two rings. So none of the three-way junctions can connect two rings. So if the system is predominantly composed by rings, then three-way junctions are not possible. And this was quite interesting. So we first characterized the junctions, and then actually we developed a model which allowed us to consider higher densities. We are not yet at the level of percolating networks, but we are at the level of one defect containing structures, and we managed to show a quite clear two-way scenario of a structural transition on cooling in dipolar hard spheres, which we now can guarantee it takes place exactly in this way. At low densities, you go through chains into rings, and then rings start merging, but the junctions are four-way junctions, necessarily four-way junctions. Alternatively, at higher densities, Y junctions are extremely entropically nice. They are really good, but they exist in a very narrow range of temperatures, and they basically give up in favor of ring formation, and they're suppressed by, again, four-way junctions. So it's kind of a thing, and again, there's no trace of a vapor-liquid transition. All these structures are not compact, they are not droplets, so it's not really the second order phase transition, not the first. There's no divergence here. That's the story of dipolar hard spheres, and now in the remaining 15 minutes, probably, right? What do I have? So I'm talking now for 27 minutes, probably. Yeah, so we will, in the remaining time, I would try to tell you what we did, trying to make our life a bit more exciting and go away from dipolar hard spheres. So this was our entertainment in Vienna recently, because Vienna University celebrated 650th anniversary, and we were involved into celebration activities, especially outreach activities and dissemination, and that's always exciting, right? You talk to kids in German. Great. And my group enjoyed it strongly. And it was plus 35 outside, and we were in plastic pavilion. Great. Great experience, but still rewarding, actually, I have to say. And for that kind of event, we on the 3D printer, we printed prototypes of the particles we are studying. So they are of this size. So what you see is a picture, actually, of the table of my PhD student, who was filing them with a nail filer, because they were actually separated in halves, and inside there were magnetic bits. So you can see that they're cubes, ellipsoids, then these funny things, and then finally spherical particles. And they form funny structures, most of which are actually still ring-like or bracelet-like structures. And why did we do that? Because we wanted to, so initially, the idea was, let's try to see two ways of screwing up the system of dipolar hard spheres. The first one is to screw the idea of a sphere. Let's say, no, I don't want spheres anymore, or whatever, I don't want point dipoles in the center, I want something else. And here you can either remove the dipole from the center, or use a weird shape. Alternatively, you can say, okay, no, fine, spheres are good enough, but let's change the carrier. Let's change the interaction of these particles with the carrier. So we can what? We can incorporate them into a polymer matrix, So imagine a hydrogel with magnetic particles in, you apply the field, and there is a magneto-elastic coupling, they start rotating, they deform the matrix, so it's kind of a magnetic gel. Or, as we know, the chains are good, let's actually cross-link the chains and create some kind of magnetic filaments, magnetic chains like made of beads, and maybe that would allow us to tune a bit better and to control a bit better rheological or magnetic responses of the system. And we tried both ways, analytically and numerically. And let's first look actually at the work we are doing with my friends here in Mallorca. And this is trying to cross-link spherical particles into kind of linear objects, which we call magnetic filaments. So what we keep necessarily the dipole-dipole interaction, the soft sphere interaction so that beads of the chains don't penetrate, but we try to cross-link them in a way that the dipoles can be either, like, that there are two options to cross-link them. So we can, let's not think about it now, let's just look at this chain. So these bonds here between the neighboring particles are permanent. So it looks like a self-assembled chain, but these bonds cannot break. Even if the temperature goes high, and at that regime you wouldn't see any chain formation in a self-assembling dipolar hard sphere system, here this chain would remain due to pure mechanical bonding. This system can be, I would be very accurate on that, they can be realized experimentally. People are desperately trying to do that. There are several reports on the success. We are waiting for like a very stable, reproducible experimental system in this. In the meanwhile, we decided to see what kind of magnetic response we should expect, and if there is any advantage of actually cross-linking these particles. And earlier, Joan, Pedro, and Thomas actually proposed these two types of coupling. So two types of cross-linking. The first one was just to connect the neighboring particles in a chain by harmonic springs or by Fene kind of bonds, so that Fene means that you can't actually, so a harmonic spring is infinitely stretchable and Fene is just finitely stretchable. That kind of understanding is more than enough. And here in this model, the dipoles, the orientation of the dipoles is not affected by the presence of spring. So actually, basically, the dipoles can freely rotate. And it means that at high temperature, they would be decorrelated again. So they would fluctuate. Instead, the second alternative is to link the particles in such a way by these springs that actually rotation out of head to tail orientation is penalized by the spring, not only by the dipole interaction, but also by the spring. And in this situation, you can imagine that spring, okay, the stretching of the spring is lighter when the temperature is higher, but even at rather high temperature, when the dipoles would have been totally decorrelated, this spring holds them together. So what you expect a priori is that this system would be closer in properties to a self-assembled, like system of dipolar hard spheres, but this, at least at high temperatures, should show something else. And we looked at two quantities, and one is the dipolar correlation coefficient, and another one is the main contribution to the initial susceptibility, which is mean square dipole moment. And we developed a certain analytical model to describe in both types of coupling both values, so C and M. And we obtained basically a predictable result, namely, if you look, so this is model 1, which is supposed to behave basically like dipolar hard spheres. So the simulation results for the filament chain is in symbols, and the dipolar hard spheres are basically like in dashed line. And you can also include bonds and include softness, and then what you get is basically this curve. So at low temperature, the total dipole moment is converging to 1. At high temperature, did I say low? At high temperature, you basically, what you see is that the dipole moment per particle is 1, which is the value of itself, which means that there's no collective magnetization whatsoever for a chain. Then it grows, like the initial susceptibility of a self-assembling system. It grows, and then you see there is already familiar maximum and a drop, and this is related to the fact that the poor filament just closes to a ring, and that's it. You see that for the same range of temperatures, you don't really close this filament because it's more rigid, right? So any kind of reorientation of the dipoles is penalized. And here you see a much higher response at high temperatures, which you would expect, and still no closure at lower temperatures. The take-home message from this study, which I would like you to remember before looking at this slide, so don't look at it, is the following. Basically, if you want to have a stronger response at higher temperature, you don't let the system to self-assemble because it won't, but you cross-link properly your particles so that you induce an additional correlation on dipoles by mechanical coupling. That works. Don't go to too lower temperatures, otherwise the closure transition would anyway take place. What you can do with filaments in general, what we are currently doing, is you can functionalize the surface with a film, create a magnetic filament brush, and then with a field you can stretch and, on the contrary, collapse this kind of brush. And first, before studying the influence of the magnetic field, we decided we'll look at the properties of such kind of magnetic filament brush at zero externally applied field. And it was very interesting to discover that due to dipole interactions, well, first of all, we already knew what kind of junctions we are supposed to see. And these junctions are very different from those which can be observed in a non-magnetic brush. We used graph theory to characterize this kind of junctions. And we discovered that dipole interaction, due to its directionality, actually works against thermal fluctuations on one hand, but on the other hand, in such a brush, the dipole interaction leads to the fact that the dipolar brush is much more compact. The same conclusion was observed also for polyelectrolyte brushes, or for kind of Stockmeyer polymers. But here you can very nicely, and it's a clean experiment, or whatever, brain experiment, hope it doesn't sound too rude, of how actually pure dipole-dipole interaction would alter the properties of this kind of brushes. And so to close this part on filaments, I just show the movie Pedro did. Also, I think, no, it was not for the celebration, it was for other outreach activity. But here you can see this kind of polymers, which are non-magnetic. And these particles here, actually, they are magnetic beads. And then this brush has these yellow particles, which are, say, functionalized particles, attached to the chains with magnetic beads. And Nat? Nat? Can I play it again? Yes, very good. And the arrow shows actually the orientation of the magnetic field. And you see that by means of an external magnetic field, you can hide functionalized particles and like push them outwards again. So if you want to create a certain functionalized surface, that might be a method. Okay, so this is about filaments. I mean, you have indoor specialists in that, and they would gladly share their knowledge with you in case. We also did a lot of work on magnetic gels. So we incorporated magnetic particles into polymer matrix. It's a completely different story. It's like, I would not focus on that. I just want to say that there's a very active study nowadays going in the field. And in principle, if somebody is interested, might address this kind of systems now rather well also numerically and analytically. Talking about any kind of anisotropy and finishing actually here, the very last part of this talk is, as I said, you can either really alter the shape or the internal structure. So internal structure usually leads you to something which is called Janus-like particles. And what is like Janus due to the double-faced God? So traditional Janus particles are hydrophobic, hydrophilic. In our case, they are half magnetic, half non-magnetic. And they would exhibit various properties depending on the orientation of the magnetization. So if the magnetization is pointing perpendicular to the Janus surface, so like that, then it's a one-type structure. Usually, if the complete bulk part of the hemisphere is magnetic, then the easy magnetization axis is actually the long one. And then you will get the magnetization along the chain, and then you have this kind of staggered chains or zippers self-assembled from them. And then you can alter the shape and do cubes and ellipsoids. We did all types of these particles analytically and in simulations. So we did cubes, ellipsoids, and in principle, you can see rather interesting effects of the violation of steric interactions. And basically, in this case, the only tool is you keep the dipole interaction as is, and you just change the steric potential. I just show you that it is not that funny as it seemed in the beginning, because for anisotropic particles, to find the proper steric potential is painful. I mean, both for simulations and for analytical models. So if you want to write a Hamiltonian with, say, Gay-Barnett potential, that is not enjoyable at all. But it can be done, and then you discover actually a quite interesting thing, namely, you come back to the same problem. So, in the ground state, after like a certain elongation of these ellipsoids, you will get, instead of chains, closed structures. What does it tell us? It basically tells us that, again, even if you alter the shape, it won't really help for the magnetic response. Why? Well, because they are closed structures, they have zero dipole moment. They won't react to the magnetic field. So self-assembly would again screw, at the end, the magnetic response. That was a bit frustrating, and we checked it at room temperatures. And yes, you can see the formation of anti-parallel pairs in elongated ellipsoids, and you can see that with elongation, basically the initial susceptibility drops. And so the conclusion is simply don't make particles elongated. Like, stay with hard spheres. Want to have a response, stay with hard spheres. Or if you actually don't want any kind of strong magnetic response at low temperature, then elongate your particles. They would basically not self-assemble, but at high temperature they would be still, I mean, it will be a magnetic material, right? It will be magnetizable and demagnetizable, so everything will be fine, just self-assembly would be highly suppressed. And finally, if you try to violate the internal position of the dipole, you can basically do many things. You can do, as I said, two types of orientation of these dipoles. And I would just show you one. So it's the same method, right? You keep now the steric potential, it's a sphere, and you modify the magnetic interaction. And in this situation, you also need to be careful in your numerics, because now the forces and the torques are applied to the point which is not the center of mass of the particle. So you need a certain trick to transfer. There might be different approaches. We use so-called, like, we introduced virtual sites, and we transfer the momentum through these virtual sites to the center of mass of the particle. So that it's a mathematical trick, but it's needed. And what I wanted to say that in this case, the distance between the centers in the dipole interaction, so the dipole-dipole interaction becomes extremely complex due to the fact that the distance between the two dipoles now depends on their orientation. So if before we only had the dependence of the distance between the dipoles on the position of the centers of mass, now as long as the dipoles are shifted, you have, depending if they are oriented, this one can be oriented like this, and if this one is here, then the distance is different, even if the particles themselves are at a close contact. And a very interesting observation was done for this kind of magnetic Janus particles. This is just the last study we did really several months ago. And it was, so the interesting thing about that was what kind of variety of choice in self-assembly you can reach if you just shift the dipole slightly outwards. You start shifting the dipole parallel to the division plane outwards, and then what you get first of all, you get the transition from a head to tail to this kind of inclined and then finally anti-parallel position for two particles. And for three particles, you have a complete variety, a complete zoo of structures. So ranging from a chain to kind of this anti-parallel pair and a degenerated direction. And we did parallel tempering for larger clusters and some analytical calculations. And we discovered that basically at higher shifts, where the magnetic interactions are very, very strong, all the structures which form have zero dipole moment again. So it's very interesting, and the only thing which can break the symmetry in these closed structures is actually the applied external field. And here you see, so I call them frog eggs, because they look a bit like eggs of the frogs, but they're actually Janus particles. And here the shift grows and here the field grows. We did kind of an extensive simulation study. And you can see that at very high shifts, at rather low fields, the field is not able to break antiparallel pairs and close dipoles. Instead, if you increase the field, you would observe this kind of Zipper-Sturget chains, which they observed in the experiment. And this allows you to actually tune the field in the experiment. So which kind of field strength you actually need to control the self-assembly. Okay, we are done. And in this case, the conclusion is also very interesting. So I think that the story of today tells us that you really need to think hard to push the system towards higher magnetic response after a certain temperature. So the nature somehow provided us with magnetic materials which tend to close the magnetic flux in such a way that at low temperature it minimizes the energy and it doesn't react to an external field. And basically, so far, we know only two systems which can enhance the magnetic response. And one of those we suspect to be magnetic cubes with this kind of orientation of the dipole moment. It's work in progress, and it's difficult now to say whether it's really true or whether actually the crystalline lattice would form eventually. That we don't know. And we know that at higher temperatures, before the closing, a certain proper way of mechanical coupling between the neighboring dipoles would lead you to the enhanced response. Otherwise, no way. Shifting dipole outwards, no. Elongating the particles, no. That would always lead to a magnetic flux closure. And as a result, to the drop of the initial susceptibility. This is almost the complete group reunion in Palermo recently. So these are people who basically did the job. So I'm not really participating. And so these are people I'm highly grateful to for all these contributions you saw today. And of course, I would like to also thank Thomas and John for me being here, and all my collaborators whose contribution you also saw today. Some funds, so namely the Austrian Scientific Fund, Vienna Scientific Cluster, and Russian Fund for Basic Research, and you for your attention.
Thank you for your talk and illustrative talk. So if you have any question now?
This is a very side point, but I was a little struck by something you said in the introduction. You said magnetic, I mean, this kind of magnetic.
That I did, yeah, that I can imagine.
Then you mentioned DNA origami. I was struck because DNA origami and there's no magnetic interaction.
No, sure, no.
So it was.
Okay.
What's the connection?
That is correlated with magnetic filaments story. We are working now with a group of Oleg Gang, who is actually an expert in this DNA origami. And they are trying to do the following. They are trying to, you can take a magnetic colloid and functionalize it with DNA. This is no problem. You can take another colloid and functionalize it with DNA. And then, in principle, you can use a trick of DNA origami, which theoretically sounds very nice, because so what is the basics of DNA origami?
Yeah, I think it's better to explain.
Yeah, so what's DNA origami, right? What's in the background? We did also some work on self-assembly of blunt-ended DNA duplexes. So DNA, depending on where you cut it, would be very selective to self-assemble. So if you take DNA and cut it in various places, then the remaining, basically, end would attach only to an end corresponding to the sequence. So basically, you can very nicely control the amount of functionalized points. So if you make a star, it will be a very classical prototype of so-called patchy colloid. So you do like, say, A would connect only to A and B would connect only to B. So, and if you want to do something like, I don't know, you synthesize that's the last thing which Oleg actually shown in Vienna Summer School on soft matter. That was fantastic. They made a Leonardo da Vinci man out of DNA origami. So basically, you make building blocks. So and you need, say, this connects only to A, this connects to B. And then you make a brush which has B, and say C, and then this would be arms, so you connect it. You basically drop everything in solution, and B would connect only to B. So this B bond is blocked. Now you add in the next AB cut piece, and that would close this bond. So you would have two arms. Then you need something which will connect, say, a ring segment, which would have a C patch, and it will connect to a C patch and will make you a head, and so on. So this kind of things they can now do with really properly chopped DNA. And the funny thing about this is that, so when you see it, you say, oh yeah, that can't be true, right? Just like you can't do it. You need like, I don't know, and it's a commercial technique nowadays. So Oleg told us that a bachelor student needs like 3 weeks to learn to do this. I mean, then you need to know how to chop, then you need to like pay lots of money to buy properly chopped DNA, properly, like proper device, but you can do that. And now you ask, okay, great, that's what I need for creating magnetic filament, right? I just cover it so that it's like, here it's only A's, there is only B's, and then I just like connect them. And now comes the tricky part. DNA by itself is very, very good polymer. It's a very like easy to deal with polymer, besides being biological, biocompatible and everything. Now you start adding their magnetic particle, and all possible troubles start. Not sufficient coverage, van der Waals forces coagulation. They are much stronger than the DNA patchy interaction. Second problem, okay, you functionalize them, fine. You cover all the like surface with DNA strands and they attach. But then the density is so high that the distance between the magnetic beads is so big that they are not interacting anymore. And there is a very like, so there is a potential, but it's rather difficult. What you can now do, you can do a non-directional self-assembly with the help of DNA origami. Basically but then you're not very picky about types of patches you have, but you can do that. That you can nicely do. So, but this is isotropic. So then you can't really control. You can still do it in the external field, so that chains preform by itself without patches, and then you anneal system slightly so that the activation barrier of the DNA attraction is overcome, and then they stick to each other. But I mean, there's a lot of chemistry behind which is not there with DNA origami, pure DNA origami, and which is immediately there when you add like metal particles. With gold is better, they say. I don't know why. Oh, it's more. It's less reactive. I'm not a chemist, so it's for me difficult to say. But that's to the best of my knowledge.
Okay.
Do you think would it make sense to consider a few magnetic moments per particle? If I understood correctly, you will always consider 1 point magnetic moment.
It's a brilliant question. It's a very good question.
Or even continuum distribution of magnetization.
It's a really good question. I'm very happy you asked. I tell you why. Magnetic Janus particles, I talked about in the end. And I mentioned that you can make the silica particles covered with a cap. And initially what we did exactly one shifted dipole on the surface, and we managed to reproduce very nicely experimentally observed structures. And this story was all very happy, and we thought, because I calculated first, depending on the thickness of the cap, the continuous distribution of dipoles. I looked at the pair potential and said, no. We start with one dipole. And it worked all good for 3 years until we actually went to the lab. Then we went to the lab, and 3 theoreticians came to the lab. We were given laser tweezers. We could move magnetic colloids. We started moving them, and I was like, But these structures you didn't report, and there were so many metastable configurations, or maybe stable configurations, which were completely open. So we only saw compact structures in the simulations and analytically predicted. Instead, there were like structures, for instance, like a Mickey Mouse, so two colloids like that and one in the middle. And that cannot be described with one dipole. There's no metastable state like that. And then it was kind of a feeling of nightmare that like that continuous distribution was coming back. But you know, it's good to have PhD students inclined to do simulations. So we said, let's first try with 3 dipoles. And that worked. So far it seems to work. So you need extended dipoles for Janus particles, necessarily. So for any kind of this internal anisotropy, you need a more complex interaction. Otherwise, you don't reproduce really the structures.
Any more questions? So we thank again our 3 speakers.
So I gave back everything, right?